Hi guys, it's your guy Olumide, and today we're gonna be solving another one of the most commonly asked tech interview question, and the cutting wood question. So it's a DSA problem that's commonly asked by top tech companies including Google, Amazon, Netflix, Meta, Apple, Microsoft, and other top tech companies. The problem statement states that you are given an array representing the heights of trees and an integer k representing the total length of wood that needs to be cut. So we'll be given an array, just like in this example here. We are given this array heights, you understand, is an array of heights of tree. So meaning that each element in the array represents a particular height, which is visualized in this graph. So we see that this is the first tree, and it has a height of 2, just like in the first element of the array. The second tree will have a height of 6, and this is it right here. Right here having a height of 6, and this is the third tree having a height of 3 right here, and this is the fourth tree having a height of 8, as we can see right here. So the last tree. So now for this task, a wood cutting machine is set to a certain height h. So this is the wood cutting machine now. It's a machine that the blade of the machine is set to a certain height h. Now the machine will cut off the top part of any tree taller than h. So just like being realistic, whenever we're trying to cut a tree, anywhere we situate the blade is where it's gonna cut off. The remaining parts downward or to the bottom, to the roots, will just remain untouched. So, and the wood cutting machine, if we set the blade to we're gonna be setting the blade to a particular height h, and the machine is gonna cut off all parts of the tree that is taller than h, while trees that is shorter than h will remain untouched. Now and now we are now asked to determine the highest possible setting of the woodcutter h so that it cuts at least k meters of wood, and we are asked to assume the woodcutter cannot be set higher than the height of the tallest tree. So what they're asking us to determine now is the highest possible setting of the woodcutter that will make it to cut at least k meters of wood. Don't forget, we'll be giving the heights, and we'll be giving k, that is the meter of wood that we need to cut to make a fire. So, and then just in this example, the heights, the settings, the wood cutting setting h that we will need to place our wood cutter so that it could cut off at least k amount, and k meter of wood is 3. Why we place it at 3 is because fine, one thing is that we can place it anywhere right from 0 to 8. I mean the wood cutting machine. The question just told us that we should assume that we cannot set it higher than the tallest tree. So the height that we can set this wood cutting machine actually now could be anywhere up to this 8, up to this height, the height of the tallest tree. So, but we have advantage of setting it anywhere at 0, at 1, at 2, at 3, and anywhere we set it is gonna cut off every tree to the top of it. And what I mean by this is that look at this particular first tree here. Its height is 2, so it's not even up to the height of the height that we set the wood cutting machine to. So imagine this one now, its height is 6, so we set it at 3, meaning that we are able to cut off 3 meters of wood out of this particular second one. And then look at this third one here. This third one also have an height of 3, so therefore we could not cut anything. Why? Because it is placed at exactly the edge, so it's unable to cut out anything. And look at this right here. It has a height of 8, so placing it at 3 is enable us to cut off 5 meters of wood off the top of the tree. And because of that, when we sum up the total number of wood that we cut off, we have 8. So, and that means that 8 is the answer. Why? Because we are asked to determine the highest possible setting so that it cut at least k meter of wood. What that means is that, okay, fine, one thing you really need to know is that we can set our wood cutting machine to this 0, and whenever we set our wood cutting machine to 0, we are gonna be able to cut off the whole tree. Look at setting to 0 now. The shaded part, anyway, you see the shaded part just like this now, it means the part that was able to cut off by placing the height setting at a particular level. So when we put the height setting h at 0, that is, we put it at the very bottom, at the very roots of every tree, it's gonna be able to cut off every one of them. And look, it cut off 2, cut off this 06, cut off the 03, cut off the 08, and that's the most cut wood is 19 in this case. But when we place it at the very top, right, it's gonna cut off just 0 amount of wood. Why? Because we place it at the topmost, so it's unable to cut off any wood realistically. So the most amount of wood is cut at h equals to 0, where all 3 are cut from the bottom, while the least amount of wood is cut at h equals to 8, when no wood is cut at all. So we can say that moving our the value of h, or the wood cutting setting, from the point 0 here to the point h, we yield lesser and lesser wood. So if we put it here now, we're gonna be yielding, that will be 2 minus 1, 6 minus 1, everything here minus 1. So you understand, and when we put it at the very top here, it's gonna yield 0. So placing it, as we adjust it from 0 to 8, it's gonna be yielding less and less wood. And the problem statement wants us to actually find the heights that we will place our h, the highest height that will place our h, such that it will yield at least k meters of wood. And what that means is that, you see, we can place our height here. It's gonna yield 19 meters, 19 meters of wood. When we place our h to 1, it's gonna yield fine. It's gonna yield less than 19. Let me say 19 minus 1, 2, 3, 4, because it's gonna be reducing h by 1. So that is probably 15. So, but we say that 15 is still greater. It's still up to the k. It's still at least k, and our k at this instance is 7, just like we can see in the problem statement here, is 7. So at least 15 is still greater than k. So when we shift it again to 2, it's gonna remove 1 again from each of them. So it's gonna be reducing like that. So, and we realize that what the problem statement wants us to find is the highest value of k. That is, we should keep raising k up enough until it gets to a point whereby if we raise it again, it's not gonna give us at least k meters of wood. It's not gonna cut at least k meters of wood. So you want us to return the highest value of k that is gonna cut at least k meter of wood. Yeah. Now we need a function that will help us to determine if a particular height setting will give us will give us at least k meters of wood. So don't forget, like I said, we have varieties of position we can place our k, including 0, 1 to up to the last the highest height of the tree. So we just need a function now that we just pass a particular height, 0 or 1 or 2, and passing the k that we're actually finding. So which means that the height that we need, and when we pass in this particular height and the k value, is gonna return whether true or false. That is, whether it's gonna give us, don't forget that it's either gonna give us or it's not gonna give us. All of this up to this point is gonna give us, but right from 4 is gonna be less. Why? Because here it's not gonna give us anything from this index 0. It's gonna give us I think 2 from this in this index. If we place our quarter at 4, 6 minus 4 gives us 2, and right here 8 minus 4 gives us 4. So 4 plus 2 gives us 6, which is less than 7, which is less than k. So it's either we have a true, or we have a false. So look at how we apply our cut enough wood now. You see that when we place our h at 3, let's say we place our h that we pass to the function is 3, we say that it's gonna be 3 minus 6. Well, 0 meters is gonna evaluate for this one that is at 0. Why? Because it doesn't even, the tree is not tall enough to height 3, but for this particular tree that has 6 meters of height, in height, okay, it's gonna give us 3, because 3 minus 3 gives us 6 minus 3 gives us 3. Why? For this one that is 8 meter tall, and we position our quarter at 3, it's gonna be 8 minus 3, that gives us 5. So eventually we'll be having 3 plus 5 as the total number of wood that is cut, and that will be 8. Since 8 is greater than or equals to 3, it's gonna return true. So that is the work of the function cut enough wood. It's just gonna tell us if it's gonna return true or if it's gonna return false, meaning that if it's gonna cut at least k wood, or if it's not gonna cut up to k woods. Now applying the function to all possible value of h. Don't forget, all possible value include 0, 1, 2, 3 up to 8. So applying the function is gonna give us this particular boolean values. So where from h equals to 0 to h equals to 3 we continue to yield true, while h equals to 4 to h equals to 8 we yield false, which is very correct. Very true that if we place our woodcutter at 8, it's gonna yield absolutely 0. If we place it at 7, at 6, at 4, is gonna yield less than, we just evaluate for 4 now. 4 will give us 6, which is less than 7. So from 4 upward is gonna give us from 4 upward is gonna give us false, but from 3 downward is gonna give us true. Now in solving this problem up to this point, we can decide to cut enough wood on each value of h from 0 to 8, you understand, until we get to the last value that we return true. The last value will be keeping count and storing the variable. So if this one return true, we change the variable to that index. If it return true, we change the variable to that index, and when we get to a point whereby it will evaluate false, we can return. You understand? We can return and loop out of the loop, so that we can loop out, so that okay, what I'm trying to say is that fine, we iterate through this loop now by calling cut enough wood on each of the index. So this return true, we are gonna save a variable to represent 0. We are gonna go to this one now, gonna save a variable to, we are gonna update that variable to represent this, gonna update it, and when we get to this point, we are gonna loop out. We are not gonna update it, we are gonna loop out, so automatically we know our h is 3. But you see, that's gonna take a linear time. Let's talk about when we have a length of trees to be like 1 million trees or 500,000 trees. That's gonna take a whole 500 trials. And let me say that if the last element is toward the end, or even what about if k is 0? Look at the situation, a scenario whereby k is 0. Definitely h equals to 8 is gonna be the answer. Why? Because it at the top of the highest tree is where no tree at all will be cut out. So imagine you have to loop out the whole length and the whole length of the array. So, but one thing we can realize here is that this particular stuff is ordered. If you look, it's quite ordered. Why? Because you cannot find true before in between the false. It's always gonna be true, then false. I don't even understand why. Because at the point whereby it doesn't cut off, at the point h equals to 4, every other thing above h equals to 4 is not gonna cut out, because it's just reducing up to the point whereby the number of wood that is gonna be cut off will become 0. Hope you understand. So, but right from h equals to 3 downward, is gonna cut out. So meaning that if it's gonna cut out at this point, well, we don't know if it's not gonna cut out or not, because it depends on the height of the tree. But if it's not gonna cut out from this point, it's always gonna be followed by a false. I hope you understand. So it is ordered, and then a binary search could do. And we know that a binary search actually has the advantage of running in log n time, which is very, very fast and efficient than the linear time. So let's try to see how we can solve this in a binary way. Now the goal is to look for the last value of h that's called at least k wood, that is the last value of h that satisfies that condition. So we can say that we are effectively effectively finding the upper bound of the condition, meaning that a lot of condition might satisfy, a lot of value might satisfy that condition. A lot of settings of h 0, 1, 2, 3 can satisfy the condition, but we want to find particularly the upper bound, the last value, that is the one to the right. So therefore, just like we explained in our previous video, we've done a couple of videos on binary search, and we actually talked about why we do use mid position, different mid position for different bound. If we are finding lower bound, we don't need to use we just have to use left plus right divided by 2 to represent the middle position that will be selecting in our search space. But if we're gonna be using the mid, we are gonna be adding +1 to it. So I want you to go back to my previous video, even this previous one, the find the first and last occurrence of the number is actually gonna put you to understand what I'm trying to talk about here. So for the upper bound right here, we'll be using the mid position, left plus right divided by 2, so as to avoid an infinite loop. +1, don't forget, left plus right divided by 2 +1. So now we've decided to use the binary search so that it could give us a log n time, a more efficient solution. And what we'll be doing is that we're gonna be dividing our search space now. So dividing our search space, we are gonna place our search space is going to be the whole so you need to know something now, that our search space is not actually this I that is given to us here. This is 2638. You can see that it's not even ordered. So first of all, you might be thinking that how do we use a binary search technique to solve this problem? How does this problem fall under the binary search? But this with logic. You understand? Logic demand that we use it. So because though we are given some couple of number, but this number just correspond to the height of tree, but we are interested in height of tree, that is gonna we are interested in the particular height that is going to be cut when placed in any of this position. So, and we have this particular structure which is ordered, so we can go on with binary search now. So we're gonna define our search space. So, and the search space will encompass every possible height setting that we can place our h, and each possible height is height equals to 0, 1, 2 up to 8. So we're gonna place it to encompass that by setting our left and our right pointer at the two extreme of the lowest height and the highest height of the tree. You know, the lowest height is h equals to 3, highest height is h equals to 8. So putting it there now, we are going to evaluate our mid position. Don't forget how we say we are going to be defining our mid position. It is left plus right divided by 2 plus 1. So anything it give us is going to fall here. So now we are not going to check. You understand? So if cut enough wood of 4 is going to work out. So cut enough wood of because it's fall at the height 4. So we don't know if it's going to be true or false yet, but we are going to use our function to evaluate it. So it's going to give us false, because if we place our cut enough wood to this position 4 now, it's going to result in false. And what that means is that we need to move our right equals to mid minus 1. Why? Because it doesn't satisfy the condition. If it evaluates true now, we probably will set our left to mid so that we can find anything that is toward the right of it, but it is not qualified to be in our search space. So we have to set our right to mid minus 1 so that it can fall on what is before it, which is right here. So we shifted our right up to this point. So after doing that, now we find the middle value again. Because we are using left plus right divided by 2 minus 1, the midpoint is not going to fall right on this one, unlike if we are looking for a lower bound. But because we are looking for an upper bound, we are using left plus right divided by 2 plus 1. It's going to fall here. So, and that's why we have our mid position to be right to this side, biased to the right, so as to avoid an infinite loop. So don't forget that what we are just trying to do is in selecting a mid value, we just want to select something that is in the middle. So if you select this, you are gonna get to the answer eventually if you select it, but we are taking use of the fact that it is a sorted array and the fact that we are using binary search. So we want to situate it at the middle so that it could give us the answer fast, so that it can cut off half away from it, just like in this case. Because we place it in the middle, it's able to cut off half away from the search space. So that's essentially why we want to set it at the middle position. So now at this point whereby it fall at h equals to 2, we are going to check again to see if it's going to give us a true or false. Now it gives us a true. Why? Because at point h equals to 2 here, at this point it's still going to give us at least k wood, even more than k wood. So, and because of that, we are going to set our left to mid. Don't forget, we are not setting our left to mid plus 1 now. Why? Because we want to situate our left at that same position whereby that evaluates to true, because it has to be in the search space because it satisfies the condition. So who knows if it is even the upper bound that we are looking for. So far it satisfies the condition, we are not going to remove it from the search space. So, and that's what we did there. We placed it exactly there, and now we are just having 2. So now we are going to apply the middle position is going to fall to the right, unlike to the left, because normally if we say that 2 plus 3 it gives us 5 divided by 2 is going to give us 2. When we truncate, 5 divided by 2 is going to give us 2.5, fine, but we can't index 2.5. We have to remove and truncate 0.5 to remain 2. So, and when we index 2, it's going to give us left. But if we do it this way, if you watch our previous video, you know that it's going to result in an infinite loop. So we are going to, that's why we are saying that our mid equals to left plus right divided by 2 plus 1, so that it's going to shift it to this right. So anyways, we are just placing our mid position. It doesn't really matter, and so far it's inside the search space, so, and it's inside. So what we're going to do again is that we're going to set our left equals to mid. Why? Because the value is true. You understand? When you send cut enough wood of the mid value, which is 3, it returns true. So we're going to set our left equals to mid, and eventually they met here, and that's why we are going to return this particular h value 3. That is, h equals to 3 is the height that we can place our wood cutter so that it will give us at most is the highest height that we can place our wood cutter that will give us at least k wood. So if you see that if we place our wood cutter above it now, you see that it's false. So that's the highest height that we can place it. So there are two cases that we can actually, that's the logic. So I just want to give you a summary of what we did so far. We have two cases. The first case is when it when cut enough wood gives us a value of true. So don't forget that by calling cut enough wood on all possible value of h 0 1 2 3 up to 8, it's gonna give us either true or either false. So we want to look at what we do in these two cases. The second cases is when it does not give us true, when it gives us a false. So in the first case, when it gives us a true, what we want to do is I want to set our left equals to mid. Why? Because that position whereby it gives us true should be included in the search space. And why we are setting left to mid and not right equals to mid is because we want to find the upper bound. So by setting left equals to mid, look at it now, it gives us true, right? Look at this example, it gives us true. We're going to set our left equals to mid. Why? Because we want to find the upper bound to this side. So we want to check if there's another one that will give us a true to this side, to the right. But if we can set our right pointer to true here, and it's cancel off everything here, there's no how we're gonna be getting an upper bound. Everything we'll be getting is just a lower bound. So we have to set our left to mid in such situation whereby the mid value evaluates true. So the mid value evaluates true, we want to set our left equals to mid. But in the situation whereby the mid value evaluates false, look at this situation. What we do is that we set our right equals to mid minus 1. Why? Because don't forget the order of the array, or let me say the order of this particular array that we talked about, is such that if it evaluates true, if it evaluates false, everything following it is going to evaluate false. If the height setting at h equals to 3 evaluate false, definitely h equals to 4, 5, 6, 7, 8 upward is going to evaluate false. So we want to narrow our search space to right equals to mid minus 1. So it's going to come here, and then we can continue. So that is just at this point again, we are going to find our mid. Then depending on whether our mid is a true or false, we are going to follow the first case or the second case of setting left equals to mid if it is true, or setting right equals to mid minus 1 if it is false. So we can just conclude that at this point now, mid is going to come here, and when it come here is true, we are going to set our left equals to what? Mid. And then we are going to find the mid again, it's going to come right here, and because it is false, we are going to set our right equals to mid, and they are going to meet eventually, and we are just going to return h equals to 1 to be the answer. So that's how simple we can solve this problem. So we are going to be going to the code implementation now. Let's go into the code implementation for our cutting wood problem. So we are defining function cutting wood, and we'll be collecting the height, which is an array of integer which represent the height of each tree, and we'll be collecting the integral k, which tells us the least wood that we need, the least amount of wood we need to cut. So, and let's define our parameters, the h, the k, and we are trying to I call the function right here. So now let's go into the code implementation. So we'll be defining, don't forget we are using the binary method to solve this problem. We'll be defining our search space. And if you could remember what I told you about, that my search space encompasses, I say it encompasses right from 0 to the length of the height, length of the maximum height. So that the height of the maximum tree, maximum of height. So in that case, we treated this as 8 for this particular height. Now you see that the length is 8, so the maximum height. So that's our search space. So while left is less than right, cause don't forget, if you follow through with the logic, the point at which left become equals to right will return right at that point. They are going to meet at the upper bound where that evaluates true. So while left is less than right, fine, we want to find our mid position. So if you remember, because we are finding the upper bound, we'll be using left plus right divided by 2 plus 1. So now we are going to be calling a function if cut enough tree, so of mid comma k. So what we are doing right here is that we'll be defining a function that is going to tell us if at this point, at this midpoint, this midpoint is going to correspond to a value. Let's take, for instance, our maximum height is 8. So 0 plus 8 divided by 2 give us 4. 4 plus 1 give us 5. So if at the point whereby placing our height h, if it's going to cut enough wood at the height 5, then that's what we're trying to say. So don't forget, I tell you that we'll be defining a helper function that is going to tell us if it's going to cut enough tree. So if it cuts enough tree, then we want to set our left equals to mid so that we can find the upper bound effectively. So otherwise, if it doesn't cut enough tree, we're gonna set our right. It is out of the scope now because it doesn't even evaluate true. So we're gonna set our right to be mid minus 1, and on the long run we're gonna return the upper bound, and that is done by returning right. So eventually right and left are gonna be situated at the same position. I want to return right. So that's simply what we're gonna do. So we just need to define our upper function now. Cut enough tree. So this upper function is gonna be collecting the height h. So don't forget, it's the midpoint. So that's the height setting that I want to place our height. So which is an integer. You can just set an integer here, and also it's gonna be collecting a k integer. So and the return of this one will be a boolean. So of whether it can cut enough tree or it cannot cut enough tree. So that's what we need for that function. So the return of this this first cutting wood will be an integer, so which is gonna tell us the particular height that we're gonna set, the particular height setting that is gonna give us highest height setting that is gonna give us at least k meters of wood. So right now we collect our h and we collect our k. So don't forget that for what we want to do for this cut enough wood is that we are gonna iterate through each tree and want to start summing up the maximum height that we can obtain from each tree when we cut it at that particular setting. So we are gonna sum it up, and that's gonna tell us whether it's up to k or not. So we are gonna set our maximum height to 0 at first, then we're gonna iterate through for value in or let me say for height, for each height in our height array. So and that actually means that we will be needing an height array. So because we need to iterate through them, so let's pass it here. Height heights which is an list of integer, is a list of integer. So we'll be passing that same height to the function call, so which is here. So we are gonna be passing it here, and then fine. For height in height, we want to check first of all if this particular height value, so we need to make sure that it is greater than the height h. It is greater than the height setting. So why I'm doing this is because if it is not greater, let's say we place our height setting at 3 now, and then one of the possible height that we have here is 2. So 2 minus 3 is gonna give us a negative answer, and we don't want to even add a negative answer. So if the height is not up to that particular height, we just want to ignore it. So it must be greater than the height setting that we are looking for, so we can effectively get those heights that are above that can be cut over it. So if height is greater than height, what we want to do is that we want to sum up our maximum height. The total that we'll be able to cut now will be summed up. We add it like height minus h. Hope you understand, because we're interested in the I don't know, this is what we're trying to find really. This particular tree have a height of 2. Now imagine that the height setting that we are sending in is 3. So you see that 2 minus 3 will give us negative value, and we don't want a negative. We just want the total number of, or total meter of wood that can be cut above that particular height for that tree. Look at 6 for instance. Now let's say now for 6, you will see that the total height of this particular tree is 6. So if we send in a value of 3, it will be 6 minus 3. So we can have, after cutting it at that particular setting 3, we still have 3 wood cuts. So unlike this one whereby it's not even up to it. So similarly now this one is just equals to it, so we don't even need to evaluate it, we can just leave it. But when we come to it now, see that 8 is greater than the height setting is 5, so we can cut it. That's why we say that if height is greater than, in fact, we are not gonna put equals to, because if it is equals to it, it's gonna give us 0 anyways. It's not gonna add up to the maximum height, so it must be greater than it. And in a situation like that, we're gonna sum it up with our maximum height. And at the long run, what we want to do is that after evaluating it for every tree in the array, we're gonna return maximum height is greater than, don't forget we're returning a boolean, so it must be greater than or equals to k. So this way now we are effectively returning a boolean that is going to tell us if the maximum height is greater than or equals to k, if it is at least k. So if it is returned true at this instance, it means that the maximum height is that is summed up is greater than or equal to k. So that way we can effectively know. So, and what we are doing is that based on this value that it is greater than or equals to k, we are either gonna, if it evaluates true, we're gonna set our left to mid. If it evaluates false, we're gonna set our right to mid -1, and from there again we are gonna loop continue. So now we have been able to solve this problem. That's how we solve it. So let's run it now. So by running the code, we see that we have 3 returns, which is actually the answer. Don't forget that from the logic we explained, we see that 3 is the right answer that will give us k is the right settings of height of the tree quarter that will give us at least k7 7k, okay, equals to 7 meters. So thank you for watching so far like this. Kindly like, subscribe, and comment. Thank you.